Alrighty. This next video, this is probably one of the most important ones we're going to do in terms of gases. So important that I'm going to tell you the secret word right now while I'm thinking about it in the beginning of this and say that our secret word for this lesson is Voyager. Voyager. Okay. Right on. So we're talking about the ideal gas law. Ideal gas law is a consequence of all of the gas laws we talked about in empirical gas laws. Okay. The empirical gas laws gave us very specific things that were related to each other, and we had to hold some other things constant. Okay. You may hear some people say, or the book or Alex or something is going to come along and tell you that you could use this, which is called the combined gas law. Okay. Um, that would work if you're comparing two different scenarios. Okay. You don't have to do it that way. There's other ways to do it. The best way to do things, and the only way I think you need to be doing them for me, is to be using the ideal gas law. Okay. And we're going to show you what that is. Okay. So don't worry about combined gas law. Okay. The ideal gas law is a combination. This is born of the fruit of the labors of the empirical, good Lord, sorry, the empirical gas laws. Okay. And it relates all of the things together. Okay. And that is that P times V equals N times R times T, or PV equals nRT. This equation is so important, I'm making you memorize it. There's not a lot of equations I make you memorize, but you will not get this on the info sheet. You have to know this equation. Okay. So what does this mean? We're going to have pressure times the volume is equal to the moles times the gas constant times the temperature. R is a gas constant. The job of R is to make sure the units come out okay. It's just a conversion so that we can have all the pressure, volume, moles, and temperatures come out okay. All right. Typically, technically, it's related by energy through all this, and we can figure that out too if we wanted to. But really, you'll be given this. Okay. And what's nice is there's a value for R for lots of different units. Okay. And so this is literally what we'll have given to us. You've probably seen this on the info sheet already in your lifetime with other exams. This is given to you. So the challenge is going to be choosing the correct constant for the problem you are working. Okay. Um, and that you can really use any of them. You just have to use dimensional analysis to convert units to the right things to use the equation. One of the best things to do is to just choose a gas law that's in the units that you choose a gas constant, excuse me, that's in the units that you want. So you do as little conversion as possible. Okay. Also, don't trust yourself. The exam stress is going to stress you out. Okay. Don't trust that you're going to have these memorized. Yes, I know I have some of them memorized because I've been doing this for 800,000 years. Okay. I've seen way more students than I'd like think that they can memorize the gas law, I keep saying gas law instead of gas constant. They memorized R, or I thought they did, but had the number wrong. And so their problems are all wrong and they're losing points because they don't have the right value of R. Okay. Any of these will do. Just choose the one that works with the units you have. If you're looking to compare scenarios, which is what the individual empirical gas laws are great for, you can do that with the ideal gas law too. To compare things, we can just take PV equals nRT and divide it by PV equals nRT for the two sets of conditions. 1, 1, 2, 2, 2, 2. The gas constant is the same for each of those, so we can cancel out the gas constant. Hell, that looks just like the combined gas law, so we don't have to worry about it. Okay. If you say you're comparing pressure and temperature at constant volume and amount, well, then volume, amount, and R all cancel out, and you've got P1 over P2 is T1 over T2. Okay. It'll happen. It'll work if you want it to. We don't often do that, but if you come across something you can do that with, you can do that. Okay. All right. One more tidbit of tasty gas information, and then we can work some problems as examples. That is this concept of STP. STP, I really should have put a picture from Stone Temple Pilots, but you guys are all too young to know Stone Temple Pilots. Anyway, I think of them every time I do this because that was what they were called, STP. But STP is really standard temperature and pressure, which is not standard state. Okay. Remember, standard state for thermodynamics is 25 Celsius at 1 atmosphere. Okay. Here, STP is 0 Celsius and 1 atmosphere, and you need to know this. Okay, you need to know this too, and know that they're different. Right, this is for thermo stuff. Thermodynamic standard state. And STP is that. I really had a lot of room. STP, that would have been great. I'm sorry. I'm a failure. All right, let's start working some examples. Here we have, here's a question. This is why I brought up STP. What is the volume of 1 mole of gas at STP? This is the nice thing about the ideal gas law. The identity of the gas does not matter. Okay. So technically, and this is something Avogadro did. So we're just doing the calculation from Avogadro's stuff. It was to say that at STP, 1 mole of gas occupies the same volume no matter what the gas is. Okay. And Avogadro defined this quantity as the molar volume of a gas, or VM. Okay. Uh, Yeah, we don't use that a lot. I don't want you to memorize the number that comes out of this or anything. We just want to use this as a way to step ourselves into ideal gas law stuff. All right, so we want to remind ourselves what STP is. STP means we have 0 Celsius and we have 1 atmosphere of pressure. Okay, we have 1 mole of gas, and the question is, what is the volume? This is N. Okay, this is T. This is P. R. We should have R over here. Okay, we'll figure out R in a second. Okay. Let's take a stab here. What do we got? Let's see. Now, the only sticky point with the ideal gas law, let's go back and make sure I remember to say this. Yes, our temperature has to be in kelvins. Okay. So if you're given a temperature in Celsius, which if your instructor's kind of a jerk like I am, they'll probably give it to you in Celsius. Which is fine. Maybe they'll even give it to you in Fahrenheit just to piss you off, but pay attention. You'll be fine. Convert that sucker into kelvins. And even though it's 0 Celsius, we're still going to have to shh and shut everything off. And I bet you're not even recording anymore. Interesting. Are we still here? Okay, this will be interesting. All right. So don't bump that button again. Let's work this problem. Okay, what is the volume of 1 mole of gas at STP? So our first thing to do is we want to convert the temperature into kelvins. Okay, this will be on the info sheet for you, so you don't have to worry about it. Remember that our Celsius temperature plus 273.15 will equal the Kelvin temperature. Okay, so 0 plus 273.15 is 273.15 Kelvin. All right, now we're ready. Okay, And there's lots of ways to work your way through this, and it just depends on how you feel about the algebra. All of this can be done with the ideal gas law. Okay. And with this, we can we can choose amongst ourselves and how you want to do this. If you want to take all your numbers and plug them in there and solve it out, do it. If that's how algebra works for you, do it that way. With ideal gas law, like to rearrange the variables and then plug the numbers into that. Since we're looking for volume, we can solve this for volume by dividing by the pressure. Okay, and get nRT over P. All right. And now we know nRT and P, so we can plug all this in and say that the volume is equal to, we said at the start, this is 1 mole of gas. R, since we're at atmospheres, then we can say this is 0.082058 liter atmospheres over kelvins and moles, okay, times the temperature, which was 0 Celsius or 273.15 Kelvin, okay, divided by 1 atmosphere, okay. So essentially, we're just multiplying those two things. If we look at it and pay attention to it, our units are canceling each other out so that all we have left is liters, okay? So this is 22.414 liters, okay? Yeah, 5 significant figures, so we're good. There we go, okay? Does that make sense? Hopefully it does. Let's take a stab at another one. This matches what Avogadro said. This is the gas constant. We don't need to worry about it. Molar volume of a gas. We're not going to stress about that. Okay. Okay, here's another one. Let's figure out what the pressure is in pascals for 64.86 grams of nitrogen gas in a volume of 1.375 liters at 4.25 Celsius. So we've got a lot of converting to do. Okay. We can do our temperature first, since that's an easy low-hanging fruit. Temperature is going to be 4.25 Celsius plus 273.15 is going to give us 277.40 Kelvin. Okay, this will have 5 significant figures since we had 2 decimal places. Our answer needs 2 decimal places. Okay. The other thing we need is we had better convert this grams into moles, okay? Because we need moles. So we can go ahead and say that N is going to be 64.86 grams times 1 mole. 1 nitrogen is 14.01, so 2 nitrogen should be 28.02 grams. Again, you don't have to memorize those things. Look on the periodic table, it'll have them for you. Okay, this gives us 2.314775 moles. Okay, this should have 4 significant figures, so right there. All right. Anything else we got to do? Nah. All right. So let's take this again. We're going to write our PV equals nRT. And what do we want? We want the pressure in pascals. So we're going to solve for pressure by dividing by the volume. P equals nRT over V. We know all these things now, so we can plug stuff in and say that this is equal to our moles, 2.314775. Notice we're putting all of our numbers in, and we'll round it at the end. We want pascals, so what we're going to do is we're going to use the R. There's an R in terms of kilopascals. Let's write this off to the side so we have it. I should have put the table of R's on this, but I didn't think to do that when I was starting this out. 8.3145 kilopascals per decimeter cubed over kelvins times moles. This is R. Okay. Now, the nice thing is the decimeter cubed is the same thing as a liter. So we can do kilopascals times liters. I'm perfectly okay with that. So we're going to go back and do that now. All right. So this is 8 Ah, damn it. 8.3145 kilopascals times liters over kelvins and moles. And our temperature was 277.40 Kelvin. And all of this, dude, is divided by the volume, which we were given 1.375 liters. Okay. And when we math this out, we're going to get 3882.82832. I'm just kind of cramping my arm. And it's not even the arm I'm writing with. What the hell? 3298 kilopascals. All right. If we stopped here, this would have 4 significant figures thanks to our volume. So I'm going to mark that so we have it. Let me mark it on top. It looks better that way. Here, there's our sig figs. Okay. Now, unfortunately, the weirdo who wrote this problem asked for the pressure in pascals. This is kilopascals, so we just have to convert. Okay, we can tag our dimensional analysis on here and say that 1 kilopascal is 1,000 pascals. And so this is now to 4 significant figures, 3.882 times 10 to the 6th pascals. Okay. If you have questions about any of this stuff, let me know. Every ideal gas law problem is the same thing. Okay. You have some data you're given. You're going to convert units, use PV equals nRT, and solve for what we're looking for, plug stuff in, and find the answer. Okay. Right. We're going to do a little bit more involved problems with ideal gas law in a minute. Okay. Just wanted to wrap this up for us now. Okay. If you need anything, I am here. Feel free to ask questions and I will get at you later. All right. Have a great night.